Okay, thank you again. I mean, I already said I'm very honored and proud about this prize. And since I was asked to give two talks, I decided to change the topics. So the topic is quite different from the one we've seen before. The lectures. So the first one was more on the geometric analysis part. This one is more on the PD side, even if we would like to find some geometry in this. And I start immediately with the problem we consider. So the problem is a system of PDEs coming from variation of models. So the model now is to minimize the Dirichlet energy. We are on a two-dimensional domain, say smooth, connected, and the important part is the class of function where we do minimize. This class of function can be described as follows. I mean, it can be written as the sum of n h1 functions, so Sobolev functions in the two-dimensional plane. They should be non-negative, so bigger or equal than 0, and they should enjoy this condition, so that the product between two of these functions, uj, uk, should be 0 almost everywhere. And then, I mean, that's variational problem. We need to impose boundary data. The simplest one is Dirichlet boundary, so we fix gi on the right space of the boundary with this same condition, gi, so gj, gk equals 0, gj bigger or equal than 0, and u at the boundary equal g. So we will come back, I mean, to this model. I mean, to explain it, let me tell you where these models come from. You can see this model has a singular limit of a competition diffusion system for different species living in a two-dimensional domain. So the system is a diffusion system, so minus Laplace uj. So each uj can be interpreted as a density of a species. So they stay in equilibrium, but the interaction of a species with the other ones are penalized. And mu is a coefficient which quantifies the strength of this interaction. So these are n different species competing in the same environment, and they compete for the same resources. And in a very simple model, you can study this sort of systems of PDs. So they are density of species, so that's motivate why they are bigger or equal than 0. And the problem I'm going to talk about is a sort of singular limit as the competition goes to infinity among these species here. And indeed, what happens when the competition goes to infinity, that the species segregate. So they occupy different parts of the domain. And the problem becomes a sort of optimal partition problem. So the condition uj, uk equals 0 has to be interpreted as having a partition of our domain and be optimized by this energy, which is the Dirichlet energy for the density living on this partition. So this model has been really widely studied by the PD community. There are a series of works, so starting from, it's a free-bounded problem, so starting from the works of Alt, Caffarelli, Friedman, so starting from so the 2000 on, there are many works by Conti, Terracini, Berzini, works by Caffarelli, Brock-Joffre, Caffarelli, Lin, Caffarelli, Karajan, and Lin. Especially Lin this morning talked a bit about this problem, this optimal partition problems here, but many other problem works arriving. I mean, I will comment this because they are. I forget to say this is a joint work with three colleagues in Sapienza, so Flavia Lanzara, Giulio Montefusco, and Vincenzo Nesi. And there's some late work of Flavia Lanzara and Giulio Montefusco from which this research started. So in order to make a connection with what Lynn was talking this morning, and and also, I mean, with the previous talk, we can interpret this as an harmonic map problem too. And indeed, I think the first appearance of this problem was in this setting of harmonic maps into singular spaces. So the space, so where the maps take values. So the domain is omega in R2 in our context, or can be an open set in Rn. But the space where the maps take values is a singular space, which is the union of the semi-axis in Rn. So this one is a tree, which is, you have to imagine as made by, so that's sort of sigma 3 plus. So it's the union of the semi-axis in a tree. And you look at maps U from this domain to this singular space. As Lynn was explained this morning, so this one is a good metric space to make variation analysis because it's contractible to the origin. And so the metric is the one induced by Rn, is the geodetic distance following the axis. And with this metric, this space is non-positively curved. So harmonic maps into this space exist, they are unique. It's a good setting for this problem. Yeah. No, it's a difference. I mean, for us, omega is always in R2. Yes. You can take this one generally, let's call this in Rm, but in this talk m is equal to 2. The n here, capital N, is the number of species, so which is related to the dimension of the domain. And indeed, I mean, that's the first instance I knew about this problem, which was studied by Gromov and Schoen in the early 90s for studying rigidity into groups, harmonic maps into groups. And soon after, this theory was generalized to very general metric spaces, non-positively curved, by works by Jürgen Jost and Korevar Schoen in around 93, 97. So that's sort of the same problem. And indeed, I mean, the Dirichlet energy for this map U, since locally the map has only one component, because it lives in one axis, is exactly the gradient of the map, the H1 map in this model here. So they coincide, and that's exactly the same energy, the harmonic energy in that case and this case. But you can also see these maps here as harmonic function, harmonic maps into the values of 2 points, which is the one we discussed a bit in the previous seminar. And in this one, you can do like this. You take your function u, which was the function, the H1 function, made by the sum of the density of all the species, and you double it. You take u and minus u. And you consider the 2 points. So for those of you who were present in the last seminar, the 2 points, which are the 2 deltas in u and minus u, this function here turns out to be a stationary map for the Dirichlet energy with 2 values. And the Dirichlet energy for this map is exactly the energy we consider. And indeed, for this map here, we can prove all the regularity results we discussed for the stationary case in the previous talk, so to speak. Even if here the problem is different because we're talking about the Dirichlet energy. Okay, so this said, I repeat, I mean, what is our main object? So coming from this model for separation of species, so competing species, the singular limit as mu goes to 0 end up in this problem of harmonic maps in these 2 singular spaces. And this one, after all, is a free boundary problem, where the free boundary is the nodal set of the solution, so where the density are equal to 0. And we are interested in the description of the geometry of these sets. So we'd like to understand the nodal sets, which is the set where u is 0, or if you want, the set where a species exchange into another, what is the geometry of this set here, which is free boundary coming from this system of PDEs. And indeed, I talk about the system of PDEs because, as I was saying, these are maps into a non-positive curved space, so the solution is unique and is characterized by the Euler-Lagrange equation. And this one are the Euler-Lagrange equation for this system. So the density, the overall densities are subharmonic in all of the domain. So they are positive, and I mean, they are not zero, and I mean not negative. They assume the boundary value. They are segregated. This one was the condition. And the two equations are these. They are globally subharmonic, but if you look at the difference of one density with all the other, they are superharmonic. Which means, so to speak, that inside the nodal region, which are the domain where only one species lives, so inside here, the Laplace is equal to 0. So because it's superharmonic and subharmonic, where it does not meet the other species. On the overall, I mean, it's just subharmonic. So this problem is clearly conformally invariant. So from now on, let me assume our domain is the disk in the complex plane or in R2. So just some terminology. So where uj is bigger than 0, we call the nodal region. And then we have a notion of multiplicity, which is the number of species which are competing around the point. So, for example, which I mean should be defined by a limit, of course. So inside the nodal region, the multiplicity is 1. So because we have just one species. So if you look a point along an interface, this free boundary, the multiplicity is 2, because just two species compete around this point. But we may have points where more than two species compete, like this one here. Here, for example, we have 3 species. Here the multiplicity is 3. But we can also have 4 points, 5 points, and so on. So this one, for example, here the multiplicity would be 4, and so on. And we are interested in this higher multiplicity points, which are, in some sense, the singular points for this equation. And our question is a question of classification of solution, so to speak. So it was started in this series of works. So Conti, Terracini, Verzi, just 3 species on the boundary. Then all solutions have the nodal set which is homomorphic to a 3 points. That's the only possible solution you find, of course, up to homomorphism of your. Well, in the case the support is connected. So that's also, yes. So that's also part of the assumption, I mean, of these classical works that have been done. Yes. And these were the papers I was mentioning at the beginning by Flavio Lanzara and Montefusco. They studied the case of 4 species with connected, I mean, to boundary values. And 4 species may have only 2 types of solutions. So one single 4 points or 2 3 points. That's the only 2 configurations up to the form of this solution. And they sort of analyze, I mean, the condition to have a 4 point here. And the condition to have a 4 point here is that your boundary value should satisfy 3 integral equations, which are sort of related to this observation, that if you change so the sign of your density, so let's say here you put plus minus the density. So instead of looking at your solution, you invert so 2 signs, say u1 minus u2, u3 minus u4. This function now is an harmonic function. So in order to have aesthetic points at the origin, you need to have average 0 at the boundary, and also the derivative should be 0 in the origin. So you have three equations in order to have such a quadruple point. And your solution indeed is the modulus of an harmonic function, which is the one obtained by changing the sign alternatively to the boundary value. So in some sense, what they notice is that the 4 points is unstable. And that's it what you expect. That higher multiplicity point should be unstable. And that's our question. So in some sense, if it is true that as for the 4 points, the solution having every multiplicity bigger than 3 points are sort of not stable under perturbation. And that's our main result. So we not only prove the stability of these points, but we prove that generically all the solution to this system needs to have only multiplicity 2, so 1, 2, 3, so up to 3 multiplicity points. So the only singular points of a generic solution should be 3 points. So there cannot be 4 points like in this configuration. And generically, in the sense of category theory. So it's a countable intersection of open-dense set of solutions have only 3 points. So that's our result. I will explain why. I mean, it has also something to do with a classification problem of solution. So, so the point of view we adopt was, in some sense, was closer to this harmonic map approach. And indeed, I mean, in this four species case, the conclusion was done, I mean, going into harmonic functions. So what we consider was not only the space of n species, having these n boundary values which are connected and so on, but we consider the space of all solutions. So it's like the union of this un having n species. So in some sense, we take all function u, which can express as the sum of n functions, where n is a natural number bigger or equal than 2, with the condition, so satisfying the Euler-Lagrange equation I explained to you. So subharmonic, and the difference should be harmonic. So superharmonic. And we look at the point of analytic function theory. So we introduce, and we will use now the complex variable, and in particular we use what they are called sometimes the Wirtingen derivative. So the uz, the uz bar operator for this function. And the starting point of our analysis was, in some sense, to connect this to harmonic function theory, and noting that every solution to this system of PDEs has the uz square derivative, which is holomorphic. So its holomorphic should be in L1. So this one is the Bergman space with an exponent 1. So the first observation was that every solution to this harmonic map theory has the uz square derivative, which is holomorphic. And this one is a very well-known fact. So this combination of derivative is sometimes called the opposite differential of the harmonic map, which in this case is just a function, because we have just one chart, this method. And it's a consequence of the linear variation of the energy for harmonic map. So starting from this observation, in some sense, the heuristic was clear for us. So we will see in a while that the multiplicity 3 points in our solution corresponds to the simple zeros of the Hopf differential. So since for an holomorphic function we have simple zeros, it's a generic condition, we can hope to start from our ops differential perturbs to a single zero differential, and then go back to the solutions of our variational problem. So the next step is given a normomorphic function to go back to a solution having, so here is uz squared, having the ops differential, which is f, which heuristically should be the integration of the square root. So this one should be the right formula to have a primitive of the square root, and then you take this sort of nonlinear projection, which is modulus of the real part. This one should be a solution to our problem. And now the main difficulties is this third part here. In some sense, it's not true that every holomorphic function is the ops differential of a solution to our problem. And actually, this set of ops differential is a very small set. So if we want to to apply this heuristic, so starting from an ops differential, modify it to have simple zeros, and then integrate it back to a solution, we need to characterize the space of ops differential for this problem. So this one is the first step we undertook in this analysis. And here is a characterization. So a function in the Bergman space of exponent 1 is the ops differential of a solution U in this space of harmonic maps into these three, if and only if this set of equations is satisfied. They are sort of integral equations. So every zeta, so z naught, so there exists z naught in our domain. We'll explain this such that when we take the primitive of the square root of this f, the real part of this primitive is 0 on all the zeros of f with the odd multiplicity. So a condition to be an ops differential of a solution like this is that the real part of this primitive of the square root should be 0 at all the zeros of f, in particular all the zeros of odd multiplicity of the holomorphic function. And if this happens, so this one actually is a solution, it's in our space of solution, and its ops differential is exactly f. So this one is a characterization of the space of ops differentials of solution. Now, just to mention this, this map I, it's not one-to-one map. So in some sense, if f is an holomorphic function which has some zero with odd multiplicity, then there exists only one solution which corresponds to this holomorphic function. Otherwise, when f is only even, assume, for example, no zeros or only even multiplicity zeros, you may find more solutions which have the same ops differential. Okay, so using this characterization, all the regularity results which were proven in the literature now come sort of as a corollary of this characterization. And this one I put here, I mean, to explain you a bit the geometric picture which is behind this variational problem. So it comes from this formula that u is the real part of the integral of the square root of f, that the multiplicity of the solution is exactly 2 plus the order of zeros of the ops differential. So here you see simple zeros of the ops differential are multiplicity 3 zeros for our solution. Zeros, so quadratic point of the ops differential are multiplicity 4 points, and so on. So this one gives a relation. In all these points, we can sort of define a notion of derivative coming from the ops differential in a pointwise sense. In principle, this solution U are just H1 function, so Sobolev function, with not a pointwise notion of derivative. But actually, the derivative has a pointwise notion because it's squared is holomorphic. So the point with multiplicity bigger or equal than 3 are exactly the critical set of our solution. So are the only point where the derivative is 0. Now, if we look at the nodal sets, the nodal set is the structure of the nodal set for harmonic functions, or if you want, for holomorphic function. It's composed by non-intersecting curves, which are analytic curves, which meets with the endpoints either on the boundary or they meet on a common point, which is a critical point. So the structure of the free boundary is a net of analytic arcs which have either a common point on a critical point of the solution or an endpoint on the boundary. So this variational problem really produces a partition of the set, an optimal partition for this energy we are considering. Now, when you look at the difference between two of these functions, you remember by the characterization, this was the real part, locally was a real part of an holomorphic functions. So the difference of two values like this, it's the real part of an holomorphic function without the modulus. So it's harmonic. So this one explains why on the common free boundary, you have a sort of transmission condition. So the normal derivative, so the normal derivative, or I mean the derivative from one nodal region, or I mean seen from the other nodal region are opposite one to the other. So the picture you need to have here is that this harmonic function, they just meet with the same derivative on the nodal region. So they are coming from this side and from this side with opposite derivative. So this explains why if you take one minus the other, you see an harmonic function in your Lagrange equation. And here we have a local expansion around the zeros, around the critical set for our harmonic function. So this expansion is inherited by the solution U. So around the critical point with the multiplicity, say bigger or equal than 3, the solution is decaying like the square root of r to the h. So in particular, the gradient is going to 0 around these points. These are the only points where point-wise the gradient is 0. In a strong sense, I mean, it's you can give a point-wise limit to this condition, and you have also a rate of convergence to 0. And I forgot to say that, I mean, as for harmonic functions, these arcs meets at equal angles. So at the 4 points, they form, I mean, 90 degrees angles. At the 3 points, there are 120 degrees angles, and so on. So that's the geometric picture of this optimal partition. So which kinds, here comes the classification question, which kinds of nets can we find? We have an index formula for this net, which depends on the number of connected components of the boundary for our solution, which was coincide with the number of species in the initial formulation. Here we can keep separating in some sense. The number of species, which are the number of connected components where U is bigger than 0, which may be different from n. Now I'll show you some picture. And the number of connected components of the nodal region, they are related by this simple formula here. So that's an index, it's a sort of Euler-Lagrange, formula for this graph, which is coupled with an index formula saying that if at every critical point, at every zeros of the boundary, we associate an index I of z, which is the multiplicity minus 2, the sum of this index is exactly n minus t minus 1. So these two formulas allow us to have a classification of solution. So here I show the classification for m equals 6. Are these 7 different types. So here it shows that, I mean, the boundary may not be connected. Somehow you can have percolation from one side to the other. And you may classify, thanks to this formula, all the possible graphs you obtain for every number of connected components. number of species, and connected components of the graph. So here the graph is connected, t equals 1. Here you have 2 components, here you have 3 components. So that's a full characterization of this geometry. Now, coming back to the main theorem, which was proving that this sort of solution where higher multiplicity points arises are not generic. I explain you, how to fix this strategy. So let me sort of repeat this strategy. So we are now in the position, to find solution where the Hopf differential has only simple zeros, because we understood that simple zeros correspond to multiplicity 3 points. So we want to start from a general solution U and see that nearby this solution we find a non-degenerate solution with only 3 points. So we start from U and we take its Hopf differential, f of U. Then we modify f of U in a neighborhood of it. So we would like to find an f epsilon such that to this f epsilon we can associate a solution U epsilon. So now if f epsilon is a little modification of f, integrating back to a solution, we obtain something which is close to U. So U epsilon close to U with only simple zeros in its Hopf differential, which means only 3 points. So that's, in some sense, what we would like to prove. And I explained you that not all holomorphic functions are good for this operation. So this one is really the critical point of this construction. And let me explain this via a picture. So for example, let's take a multiplicity of 5 points, which is the real part of z to the 5 over 2. Its Hopf differential is z3. It's, in fact, order 3 0 points for the Hopf differential is multiplicity 5 points of our solution. So here is the graph. You see in some sense here this transmission condition coming from the Euler-Lagrange equation. And assume now we would like to split these 5 points into a 3 points and a 4 points. So meaning that we would like to find a close by function which is like z times z minus w squared. So a simple 0 and a double 0. So w is here, the green point, which should correspond to the 4th point, and the origin, now it's a simple 0, becomes a 3 points. Now, if you take a modification like this with a very small w, because you would like to be in a neighborhood of this function, and you try to integrate this f, the square root of this fw, integrating the square root means that we have to make a cut to this domain, and then we realize that across this cut the extension is continuous, whatever. You find that this primitive belongs to U5, so exactly as a configuration like this, if and only if, now the primitive is z to the 5th half, if and only if the angle of this vector w is one of these 5 possibilities. So in some sense, we have only 5 possibilities to split this green point from the black one in order to recover a solution with the 5 species. So the system is not so flexible. So not every holomorphic function I can use, to build up a solution. But in some sense, infinitesimally, I have only finitely many directions where I can move. So this space of differential is, in some vague sense, it's a very small set. So that's sort of the difficulty. And the proof should then proceed like this. Start from 5 points, you split 3 points and 4 points, and then you split the 4 points in other 2, 3 points, always remaining in a neighborhood of this, and this one will the singularize your solution. But each of this splitting, it's a sort of a delicate operation in this program, and that's what I explained you now the way we achieve this. So we put, so generically you can be in a simplified setting. So you may have finitely many zeros for your ops differential. Your ops differential may have an holomorphic extension in a neighborhood of your domain, and assume you would like to split one point z0 where the order is bigger than 1. So you reduce the order by 1. And by a conformal transformation using the Mobius group, you may assume that the zeros are in general positions, which means they are not aligned and they have different distances from z0. So once you are in this sort of generic situation, what we prove is the following lemma. That actually we can find for every epsilon close by solution u epsilon, which is close in L infinity and in W12, in such way that we have added one more critical point to the set of critical points. They are the same as before, plus omega 0. Omega 0 is order 0 point for the ops differential. So multiplicity 3 points, a good point for us. And we have reduced the multiplicity of Z0 by 1. And the other keeps unchanged. So it's clear that if you can iterate this process for the number of zeros you have in the end of this finite number of steps, you have untied all critical points, and you have all 3 points. And that's, then sort of reduced to a genericity, a genericity statement. So how do we do this? So actually, in some sense, we suspect our proof is too analytical. It's coming from from people in analysis who knows not much complex geometry. And I think behind there should be something which is more stable. But we do like this. So we take our ops differential, and then we write, so the usual Weierstrass representation formula. So the multiplicity of the polynomial where we have the zeros, the finite zeros, plus an holomorphic function which is not 0. And then we modify this ops differential in this way. So we split the 0, which we assume z0 equals 0. So that's zeta, so z0 equals 0, zeta to the m0, and then we add, instead of m plus 1, and then we add omega 0 as a new 0. That's clear. But then we need to perturb this holomorphic function by a polynomial, which is a perturbation of 1. You have to imagine this one is 1 plus something which is very small. But this something which is very small is a polynomial in Z with m parameters, m complex parameters, where m was the number of zeros we had. So that's the perturbation we do. And in some sense, if omega 0 is small, it's a complex number, is one complex parameter, is small. If the Wn are small, this one is a small perturbation of our f of u. Now we integrate the square root, carefully, setting up the cuts on the domain and making some manipulation to these formulas. We integrate the square root, and then we look at the value of this primitive in 0 and at the critical point zj. And if you work out this well, this, once you integrate this formula, this one becomes a linear system in this W. And the linear system is this. It's written here. So in some sense, this real part of this primitive has 0, if and only if the real part of this vector B plus matrix A times W is equal to 0. And A is the metric we obtain integrating, so the first part of this, of this expression here, and B is the one integrating, so the polynomial part, the opposite actually. So that's, the relation you get out from this explicit integration. And what we can prove is that if we choose this power of z, which remember, these kl are free parameters here. We choose this kl as a multiple times a big R, so L times R. If R is very large, this matrix here is a matrix done by oscillating integrals. We can study this oscillating integral, and we discover that for very large R, and for this choice of the polynomial, the matrix A is invertible when omega 0 is sufficiently small modulus. So this means that this system here can be solved. So we need this vector b plus aw to be a complex number. We know that b0 is a complex number because b0 is the one coming from our ops differential, which was corresponding to a solution where all the real parts were zero, this critical point. So our solution W is a minus 1 b0 minus b omega 0. And you see that now this one is small with omega 0 small because b is a continuous function. It's explicitly given by this form. So in some sense, we can reach the condition that all the real parts of the primitive at the critical points are zero by using the freedom given by these m complex parameters we have introduced in our perturbation. So this operation in some sense creates a function f, which is now this is this so let me go back now. It's once we have forgiven omega 0, we have found a w, corresponding w, such that this holomorphic function is an ops differential. So, well, if we can also manage to have real part 0 on the new critical point, which was the omega 0. So this one was not yet fixed. In the previous part, we have fixed the real part 0 to the old set of critical points, not the new one. So now we need also to take care of what happened to the real part of this primitive in the new critical point omega 0. And now everything is, in some sense, explicit. Because for every omega 0, we have found, which now I call epsilon e to the I theta, we have found the vector W, which is suited for this operation. And now I have to take care of the real part of this function at this point, which again, we come from real analysis, we see as a function of two real variables, epsilon and theta, and we can apply to this function an implicit function theorem. And here you discover this rigidity I was explaining you with an example. You find that the derivative in theta is different from 0. And actually you have k possible branches, I mean, this with k from 0 to 2 plus m0, which parameterize this equation g equal to 0, which are exactly the finite numbers of direction I was explaining you with explicit example of a point of multiplicity 5. So there are only finite of direction where we can move, so to direction theta, where we can move our point to have a new 0 to be an ops differential. Now, if we choose one of these branches, one of these directions, we know that also the real part at this new critical point is 0. So now, effectively, what we have found is an holomorphic function which is an ops differential of a solution. And now proof is finished because now this function here that we have found as a primitive for this primitive, we go back to our solution u epsilon. And now you see the order of this new holomorphic function are the one I was declaring in the lemma. So the order is unchanged for the zj, order 1 for the new 0, order reduced by 1 at z0. So this one has a real part which is 0 on all of the critical points. So it comes from a solution, is an Hopf differential of a solution. And since we are integrating a small perturbation of the Hopf differential, so the solution is closed at infinity, but it's also closed W1 because the energy are continuous in this process to the Hopf solution. And this one complete the idea of the proof. So what I find a bit strange, even if this space is a small space, our perturbation is too special, so to speak. And in particular, what sounds to me a bit unnatural is that we make a perturbation with the keep all the critical points, all the zeros, and just add a new one. And that, in some sense, is not what you would expect from a PD point of view. If you take a solution of this PD and you modify slightly your boundary value, the problem is not local because it's a free boundary problem. So all the free boundary is moving, and we cannot keep fixed the critical points for this free boundary. What we have proved with this analytical perturbation is actually that you can achieve this also with this very special modification. Okay, and I stop here and I thank you for the attention.
Very nice talk. Are there any questions? Comments?
I may not understand the talk well, but I have one question. So here you consider the several species, right? I see their distribution.
Yes.
In daily life, there's another very common example. For example, in water, we put some species, so one species, and boil, and let it cool down, and there can be some pattern. Is this similar?
Well, these models, I don't know these experiments, but these models, it's in some sense are very analytical models. They are far away from the real application, at least under my point of view. And indeed, they more serve as a model case to study the geometry of these PDs and the geometry of these patterns. So it could be that the experiments we are talking about can be described by a variant of this problem. And there are many, many variants of this problem that can be studied. So, for example, the problem Fangolin was discussing this morning was a problem where you minimize the first eigenvalues for each of these domains. You may take a variant of this problem where you don't take the boundary values, but you fix the norm, the size of this species on top of this, etc. So I would expect that this pattern can, for very first approximation, can all be modeled by something like this, and in some sense can be described by this sort of same geometry of patterns.
So here, the equations are Laplace equations.
Laplace equation.
If we add time, or temperature or something.
Well, if you so this problem is also being studied by the dynamical point of view, and indeed many of these references are also for the parabolic version of these problems, especially so the works of some of the works of Conti Terracini Berezzini, the work of Wang Zhang. They also study the parabolic case, and also the parabolic problem is well posed. So the asymptotic as time goes to zero is unique and is exactly given by this variational problem. So you can expect that as time evolves, you find also these sort of optimal partitions in the limit of time going to infinity.
Yeah, I mean,
Yeah.
some people started this problem.
Yes, yes. I don't. Yes, I don't know this model. I mean, this experiment. But you are right. I mean, I come. Yes, I come from. You know, I mean, I come from a region where we have a volcano. It's the biggest volcano in Europe. It's in Sicily. I come from the town under this volcano, and I mean, I've observed these patterns around the city. But I mean, I don't know if the model is exactly this. This I don't know.
Are there any other questions? Or maybe I'm wondering, are there results for higher dimensional domain?
So there are much less results, and the problem is in some sense I mean the point of view of the regularity, it's very much interesting. So what has been studied, for example, from the works of I think Gromov itself, Caffarelli, Lin, and others, are the multiplicity 2 points, which are the interfaces. So these interfaces are well studied, they are analytical hypersurfaces, and so on. This one is what they call the junction set. So Lin was calling the junction set. This one is also studied. There are recent results proving they are of dimension n-2, they are rectifiable and finite measure, like what we hope to prove from minimal surfaces singularities, so to speak. But there is not a point-wise analysis, I mean, for this. So we don't know what are the infinitesimal shapes around this point. We don't know what are the generic singularities in this set, and so on. And then the problem becomes more difficult and more interesting, perhaps.
Okay, let's thank Emanuele again.